what we learned in the last lecture, we saw that work done by a force, we are calculating the work done by a force F, okay, acting through a displacement. That means the force is acting on a body while it is having a displacement, or through the time it is having a displacement of S. Then the quantity work done is given by, technically it is given by the formula dot product of force and displacement, or it is simply defined as force into displacement into cos of theta, where theta is the angle between the force F and the displacement S. So before we move on to energy and power and all that, let's discuss few important properties of this concept, or few important properties related to the application of this concept. Okay, so let's come to that. The first thing is that work is a scalar quantity. Okay. Even though force and displacement are vectors, okay, but the work W is defined as what we call the scalar product, or dot product. Okay. So because when we define W as Fs cos theta, here F is the magnitude of the force, S is the of the displacement, and cos theta is also a scalar. Cos theta is just a number actually. This is the magnitude of a vector is a scalar. Cos theta is a pure number, like half, or 1 by root 2 or something like that. So work done is a scalar quantity, and of course, and work is expressed in joules for the SI unit system, or ergs in the CGS unit system. So to that end, 1 joule is equal to 1 Newton meter, and 1 erg is equal to 1 dyne centimeter. Okay. So just make a quick note of this point, then we'll move forward. Definition of work done you already saw last time. This important point here, just make a note of this first. CGS unit is a system, Adinath, which is the centimeter gram second system of units. Okay, we'll discuss a little bit about this. SI system, as you know, is the standard international system. Okay. So SI system of units, this is what is called the standard international system. Okay. So in this, length is expressed in meters, mass in kilograms, and time in seconds. So force is expressed in newtons, where 1 Newton is 1 kilogram meter per second square. Now likewise, yeah, ergs, ERGS. The unit is called erg, ERG. Okay. So CGS system it is a short form for centimeter gram second. So here length is measured in centimeters, mass in grams, and time in seconds. So this unit, we'll discuss more about it. Okay, how one erg is related to 1 joule, we'll discuss that also. But the name is ERG, erg. Just as dyne is the name of the unit for force. As you know, 1 dyne is the unit of force in CGS system, whereas 1 Newton is in SI system. So can you tell me what is the relationship between Newton and dyne? Adinath, you know that? How many dynes per Newton? Yes, very good. That's correct, Dhruv. So now, Dhruv, you can tell me how many ergs make 1 joule? Very good. That's correct. Yes, correct, Aparna. That's good. So we'll just make a note of that relationship also. That 1 Newton meter, that is 1 joule. So that is 10 raised power 5 dyne multiplied with 10 raised power 2 centimeters. So it is 10 raised power 7 dyne centimeter, or 10 raised power 7 ergs. So 1 joule of work done is equivalent to 10 raised power 7. Just as you know that 1 Newton is equivalent to 1 kilogram meter per second square. So that is 10 raised power 3 grams into 10 raised power 2 centimeters per second square. So it's okay. So this is how we find the relationship between SI and CGS units. So anyhow, that was the first point that we wrote down about work done. That it is a scalar quantity, okay, and its unit is joules or ergs. Now, second thing we want to understand here is that work done by a force F is zero if S and F are perpendicular. Okay, that is theta is equal to 90 degrees. So work done, which is Fs cos theta, comes zero because you know. Okay. Similarly, it can be negative if displacement and force are at an obtuse angle, that is theta is greater than 90. Okay. So we'll talk more about this. but first, Bhomik wants to write down the relationship for the derivation between Joule and Earth. So complete that first, and you can note down this point below also. So I'll talk more about obtuse angle, but this point should be clear to you that when theta is 90, the work done will be 0. Yeah, so Bhomik, here it is. 1 joule is equivalent to 10 raised by 7 ergs. This is the relationship. 1 joule is 1 Newton meter. So that becomes 10 to the power 5 dynes multiplied by 100 centimeters. So that's how it becomes 10 to the power 7, or you can say 10 million ergs. 1 joule is 10 million ergs, or 10 to the power 7 ergs. Is it clear, beta? Sentence A is that the work done by the force F is 0 if the displacement and force are perpendicular to each other. Okay, so the work done is 0 if the displacement and force are are perpendicular, which means that the angle between them is 90 degrees. Okay, so physically, that situation would look like this. Yeah, I'm explaining that part only. Okay. So if we have a situation where one of the forces acting on a body is perpendicular to the displacement, like for example, the normal reaction acting on this body and the weight mg. Okay, whereas suppose we are also applying a force F, like this. So now what happens is, after some time, if the body makes a displacement in this direction and reaches here after some time, so in this particular case, you will see in this example, the work done by mg will be 0, because the gravitational force is perpendicular to the displacement. Okay, the gravitational force is vertically downwards, whereas the displacement is horizontal. Okay, similarly in this example, the work done by normal reaction will also be 0, because normal reaction is also perpendicular to the horizontal displacement. But the work done by F, that will become F into S, because force is the force F is parallel to the displacement. So theta is 0 for it. So cos 0 is 1. So this example actually explains this point over here, that whenever, so this first point over here, the A part of this, that whenever we have the situation that force and displacement are perpendicular to each other, if force and displacement are perpendicular to each other, then the work done is 0. Perpendicular to each other means theta is 90. So you know that cos 90 is 0. So that's the technical reason why this happens. Okay, so this is an example of that. We come to the B part later. First, just note down this example. So in this particular case, where we are pushing a body horizontally along a surface, the work done by gravitational force and work done by normal reaction will be 0. But the work done by the force that we are applying horizontally, this force F, that will be just force into displacement. It will be magnitude of force multiplied by magnitude of displacement. Is this point clear? Don't worry about the second point B. I'll come to that. Just concentrate on the first point A first. Okay, so is this point clear to all of you? The first one, that when force is perpendicular to displacement, what will happen is our work done by that particular force will be zero. Okay, understood. Now let's come to the second part. If force makes an obtuse angle, okay, so in that case the work done will be negative. So let's understand how that happens. Okay, so let's take an example. It is actually happening in a situation. So now suppose in our example, what is happening is that the block is going to displace horizontally because it's lying on a horizontal surface. Okay, but while it is displacing horizontally, there are two forces that we are applying separately on the body. One is acting, one is pulling it in this direction. So let's say one force F1 is of 50 newtons, pulling it along this direction. But also there is another force that's simultaneously acting. Okay. And that force, let's say, is acting like this. Okay, so there's a second force of magnitude, let us say lesser, 30 newtons, but also that is acting in this way, that it's acting at an angle of say 30 degrees with respect to the horizontal. And of course, this is a block of a certain mass. Okay. Now, under the action of these forces, after, let's say, after some time, the block reaches here. Okay. So this is where it reaches after some time, whereas this is where the block started from at t equal to 0. So if the displacement from here to here, okay, this displacement vector now is, let's say, something, let's say it's 10 meters. So we want to find the work done by forces F1 and F2 on the block. And let's say it has some mass that we know and all that, but it doesn't really matter how much the mass is because we are just calculating the work done by these two forces, 10 kg or something like this. Now you can see here that we'll calculate work done as F dot S or Fs cos theta, or by definition it is force multiplied by the component of displacement along the force. So in this particular case now, for F1, the work done W1 is, let us say, F1 dot S. So that is very simple. It is F1 into S, because you can see that the force F1 is along the displacement S. The force is also like this, and the displacement vector is also like this. So it's very simple. So that work done is just 50 into 10. That's plus 500 joules. That's the work done by the first force. But when it comes to the second force, okay, the work done f2 dot s. Now let's think about this little carefully. Let's go back to the diagram and understand. f2 का डायरेक्शन देखो ऐसा है, whereas displacement का डायरेक्शन कैसा है? It's along this direction. ठीक है? So you can see clearly that there's an obtuse angle between them. So if we redraw these vectors, we can see that the force f2 is acting along this kind of direction. It's a vector that's acting like this, and it is of magnitude whatever 30 newtons. Okay. Whereas the displacement on the other hand was a vector which was along the positive x-axis. It was like this. This was the displacement vector, which is 10 meters along this. So between this axis and this axis, now you can see that it was given to us that f2 is acting at 30 degrees to the horizontal. This angle was 30 degrees. Okay, so that means now the angle between the displacement and this is this angle. This is our theta, so this is 120 degrees. So here the angle between the force f2 and the displacement is 120 degrees. It's an obtuse angle. Okay. So therefore we'll understand that W2 will be a negative quantity. Now how much it will be, let's discuss that again, but first note down up to here. So we'll see how to calculate how much it is also, or if any of you know how to calculate this, tell me how much this answer W2 will be, but otherwise just note down up to here first. Okay. So this is the second thing that we are answering here, that the work done can be negative. Okay. But for that the angle between them has to be obtuse. It has to be greater than 90, less than equal to 180. Oh sorry, yes, that will be 150. Correct. My mistake. This angle will be 150. So I'll correct this. Okay. Yes, Dhruv, very good. That's correct. Your answer is correct. Anyhow, let's write down this part first. Okay, anybody else got the answer for this part? How we'll calculate the work done? Yes, Bhageshri, very good. That's correct. Dhruv, that's correct. So it turns out that this answer will come out to be minus of 30 into 10, that's 300 into root 3 by 2. So minus 150 root 3 joules. Now ये कैसे आएगा? Let's discuss. Okay, why this will be like this? That is the main thing we have to understand here. Uh, Dhruv, just check your solution once. Huh? You might have taken the magnitude of the force as 20 instead of 30. So, we can understand this question in this way, that let's go back to the basics and understand the definition of work done. So, definition of work done क्या होता है? The definition of work done is, it is force multiplied by component of displacement along the force. Okay. So if you look at this situation above, now because S, the displacement is already in the horizontal direction, let us not disturb the displacement. Let's keep the displacement the way it is, the displacement vector. Instead, let's break the force into components. Okay. So what we had learned about component algebra earlier of vectors, that will come in very useful here. So the displacement is already along the x-axis, so let's keep it that way. So the displacement is 10 units along the x-axis in meters. This is my x-axis, this is my y-axis, suppose. Okay. Whereas the force vector, on the other hand, is in the second quadrant. So it is so this force F2 is 30 newtons at an angle of 30 degrees. So let's break this into components. So we break this into components. It has a y component of 30 sine 30 degrees, so that is 15 newtons, and you can see its x component is along the negative x direction, so its x component will be negative of 30 cos 30 degrees, so it will become minus of 15 root 3 newtons. This will be the x component. Okay, so now you can see that the displacement is along positive x-axis. Okay, and the force's x component is minus 15 root 3. So the displacement is 10 along the x-axis, whereas the y component of force is 15. But what is happening? This is perpendicular to the displacement, so work done by the y component will be 0, but this is opposite to the displacement, so work done by this one will become negative of this, so that work done will become minus 15 root 3 multiplied by 10. This is in newtons, this is in meters, so this is in joules. So that's how it is becoming minus 150 root 3 joules. Okay, so this is what we mean by saying the work done becomes negative when the angle between the force and displacement is an obtuse angle. So now you can see for the given force, the y component is, so therefore for the force F2, its x component is doing a work of minus 150 root 3 joules, and its y component is doing a work of 0. So the net work done by this force is minus. So this is the way to understand this logically. कि how come this force F2, how we'll calculate the work done by it when the displacement is in this sort of direction. So we've divided the force into two components, one which is perpendicular to this, you can see this one is along the perpendicular, and one which is opposite to this, you can see this angle is 180. Okay, so is this calculation clear to all of you? And through this, hope the concept is clear that when the angle between the force and displacement will be obtuse angle, the work done by that particular force will be negative. Bombing the part above you written down na earlier. Anyway, ठीक है. So all right, write this down properly. Yuvraj above this also. Okay. Okay, that's no problem. It's okay. So is it clear now that A part? Okay, so now let's come to the final calculation part for this question. So for the work done by the second force, this is the main important part for us here, that if we know the angle, like in this case we know it is 150 degrees, how we'll calculate the work done. So divide the force into components, one component perpendicular to the displacement, the other component will become opposite to the displacement. So the opposite component will do negative work, the perpendicular component will do zero work. Okay, so let's work out a numerical problem now. Okay, next example. So very interesting situation and important example. So we have this smooth inclined plane, which is at an inclination of some 37 degrees with respect to the x-axis, or with respect to the horizontal. So this angle here, this theta is equal to 37 degrees. Okay, and also given to us in the question, the standard value sine 37 is 3 by 5, cos 37 is 4 by 5. Okay, now what we have is there is a block which is at initially at rest over here. So we have a block of mass 5 kilograms, okay, which is at rest initially at t equal to 0. When we start pushing it up the incline, but what we are doing is, now this is the part you listen very carefully, we are applying a horizontal force on the block. We are not applying a force along the inclined plane. So we are applying the external force on the block in this manner. ऐसे करके हम force लगा रहे हैं. So as it moves up, we keep applying continuously that horizontal force. So F is a horizontal force, okay, of magnitude 50 newtons, continuously applied by some external agent from t equal to 0 onwards. Okay. So what is happening is, now after some time the block is reaching here. So at some time t the block reaches here, where let us say the displacement from this position here to this position here, this is a displacement of, let us say, magnitude 20 meters. Okay. So now, taking the value of acceleration due to gravity g as 10 meters per second square, first of all, find the work done by all the forces acting on the body. What is the work done by each and every force acting on the body? And secondly, calculate the speed v of the block at the displacement of 20 meters. When it reaches that position, what is the speed? This we have to calculate. So just try this out, people. So I'm just minimizing this for you a little bit. Okay. So understand that as the block is sliding along the inclined plane, we are continuously pushing it with that horizontal force. We don't make the force along the inclined plane. It's always horizontal. Okay. So during the time when it makes a displacement of 20 meters, now starting from rest at t equal to 0, what is the speed it reaches by the time it reaches the displacement of 20 meters? But before that, what is the work done by each of the forces? Okay, so anybody got the answer? Yeah, I'm just going through your answers. Okay, I'll just discuss. That's correct. Good. The work done, um, Dhruv, the work done by force is correct. So you should be getting the answers like this. I'll just put up the answers first, then we'll discuss the solution. So the work done by the pushing force will come as plus 800 joules. The work done by gravity will come as minus 600 joules. Whereas the work done by normal reaction, that is the third force acting on it, will be zero. Okay. So you can see that as this block is moving, there are three forces acting on it. Okay, there is gravitational force acting vertically downwards. Okay. Then there is this horizontal force that the external agent is applying. This is a force acting in this sort of direction. Okay. And there is the normal reaction that the ground is applying, or the surface below is applying. That will be in this sort of direction. Along the direction normal or perpendicular to the surface. Yes, sir. Okay. So keeping this thing in mind, try to see how you're getting these answers. Okay. We'll discuss more. So let's understand the geometry of this in little more detail. So what we should do is, since the displacement is happening along the inclined plane, we should take the direction of our inclined plane as our x-axis and take the direction perpendicular to the inclined plane as our y-axis. So with respect to horizontal and vertical, you can see this is the horizontal. So this angle is 37 degrees. So now on this block, the forces that were acting, let's come back to those. So this force that was acting, now this force was of magnitude 50 newtons. Okay, so this angle is 37 degrees. So this force will have a component along the x-axis of this much. So that will be 40 newtons, and it will have a component perpendicular to this. So the y component will be negative because it's along the negative this one. So it is minus f sine 30. So it will be minus 30. Okay. But in all of this, what about the displacement vector? The displacement vector is along the x-axis. So because the displacement is along the x-axis, you can see that you get a simple answer that the work done by the force F is F dot S. Okay. Or it is the x component of force into S. You can also understand it this way because the x component is parallel to S and the y component is perpendicular, so it won't be doing work. So either way you can see that it will be plus 800 joules. So we can express it this way or we can just express it this way, that whichever of the two methods you want to understand. So it's doing this much work. Okay. Now same way, if you look at the gravitational force, so to understand that in the case of gravitational force, what is happening is it's making an obtuse angle with respect to the displacement. The gravitational force acting on this body is acting like this, vertically downwards. Okay. So you can see that its magnitude is 50 also. Now you can see that here this angle is 37. So that means this angle will be 37. Okay. So mg has an x component which will be in this sort of direction, or y component rather in this sort of direction, which will be minus of 30, sorry, minus of 40. Okay. Mg, its components will become such that the y component, right, as minus of mg cos 37. So that is minus of 50 into 4 by 5. So minus 40. And its x component is also negative. It's acting along the negative x direction. Okay. Its x component is also negative of mg sine 37. So that is minus 30. Whereas the displacement vector you already seen earlier, It's along the positive x direction. So the work done by mg will become negative of 30 newtons multiplied with 20 meters. Or you can also understand this way, that the angle between the weight, okay, and the displacement, okay. So the angle between these two is this one. So this theta is 90 plus 37, or 127 degrees. Okay. So work done by mg is mgs cos 127. So if you know your trigonometry properly, you can also understand why this is becoming this. Okay. And the third one, you don't need to put so much detail into it, because you know normal reaction is perpendicular to displacement. So this is work done by F, this is work done by mg. Yeah, just take this down, Anshul, you'll understand. Just take down the vector diagram in terms of components, you'll understand. It's all simple geometry of triangles and all that. It's very simple.
आपण ज्या एअरटेल सबस्क्रायबरला कॉल करत आहात तो आता दुसऱ्या कॉल
Okay, people. So hope this is clear to all of you. Bhawmik, you've noted down everything now. Now it's pretty obvious that normal reaction का work done zero होगा, because you can understand that normal reaction is acting along the direction which is perpendicular to the displacement. The normal reaction acting on this body, that is acting in this direction, like this, whereas the displacement is in this direction. So work done by normal reaction has to be zero. So that's done. So one force is doing positive work, one force is doing negative work, the third force is doing zero work. Okay. Now you see that we can get the speed of the block by using this only. We don't need to apply anything else. So for the second part, we can just apply the statement of the work kinetic energy theorem. So for the second part, the first method we can go by is the work energy method. Okay. And that will be that the net work done equals the change in kinetic energy. Here I will not consider change in potential energy because I'm including gravity on the work done side. Okay. So this is the net total or sum of work done by all forces, and that is equal to half m final speed square minus half m initial speed square. That is the change in kinetic energy. This is final, this is initial. So the important thing here is that, okay, work done by gravity, that is the gravitational force mg, is included in the left hand side, that is the work done side. Okay. Therefore we will not take potential energy into consideration, because we're already taking the gravity's effect into consideration in terms of the work done by gravity. So we will not take it again in terms of potential energy. Okay. So this will become even more clear to you in a bit of time when we discuss more about potential energy concept and the formula of gravitational potential energy. So here, when we say net work done is change in kinetic energy, so in this particular case we'll say work done by F plus work done by mg plus work done by normal reaction should be equal to half mv square, because u was 0. Okay, and only three forces are acting on the body. Okay, so this is plus 800 joules, this is minus 600 joules, this is 0. This is equal to half of 5 kg into v square. So this will give us that 5 by 2 v square is equal to 200. So v is equal to square root of 400 by 5, or square root of 80, which we can write as 2 root 20, or 4 root 5 meters per second. This should be the speed by the first method. Now I'll also show you the another method where we can do this calculation by uh, by first calculating the acceleration using Newton's laws and then using kinematics. But you'll see that that is much lengthier and unnecessary, because हमने already kinetic energy के लिए काम सारा करके रखा है. We calculated the work done in the first part. So why we want to go back to again Newton's laws, do the vector analysis, first find acceleration? So that is a problem in itself. Then once you found acceleration, substitute in the formula of kinematics and find the speed. That's all unnecessary. This is the easiest method of finding the speed now. once or twice in between. Then there was a lot of noise coming from outside. Okay, last line. Can you just put your name in the login ID? The person has asked the question. No? I'm not getting your name in the messages. So just log in with your name. Huh? Just remember that in the classes you have to always log in with. Okay, and that's fine. Unmuted was fine. Yes. Okay. Yeah, so the last line is this, that the net work done is equal to the change in kinetic energy. So net work done kya hota, I've explained over here. It is the sum total of work done by all the forces. So in this case, what all forces are there? There are the three forces acting on the body. There is gravitational force mg, so that's the first force. There is the external force F that we are applying, second force, and there is normal reaction, third force. So there are only three forces acting on the body. So the work done by the first one plus the second one plus the third one, that is only the net work done. So that net work done will be the change in kinetic energy. Now change is final minus initial, but initial is zero. So it's the change in kinetic energy just the final. Now we already calculated na, that work done by each one of these. This was plus 800, this was minus 600, this was 0. So the total work done is 200 joules. So that 200 joules is what? It is kinetic energy. Initial kinetic energy was 0. Is it clear now, Bhaumik? Okay, good. Better. Now let us see the other method of solving this. Achha, I just left the calculation part, but you can see that the calculation part is okay. Now let's solve this problem by a different method, by using the Newton's laws concept. Okay. So you'll see that that method is like a revision of things we've done before, but it's completely unnecessary over here. Use the free body diagram, Newton's laws, to find acceleration, and then kinematics to find velocity. So it's a two-step process. So that is why it is avoidable. यहाँ पे नहीं use करना चाहिए. ठीक है. So but anyway, let's just quickly make a run through of it. So this force horizontally, this force vertically, and this third one like this. Okay. So these are the forces which are acting. Free body diagram बेटा पढ़ा है आपने. I have explained to you what is free body diagram earlier. Okay. So this angle is 37. Okay. Which means that this angle is also 37. So resolve the forces along your x and y axis. So take this as your x axis, the inclined plane as your x axis, the perpendicular to the inclined plane as your y axis. So on resolving the forces, you will get one component of F like this, which will be F cos 37. So that was working out to be 40 newtons. We've done this before. And you'll get the component of this one, F sine 37 is 30. Okay, so you have resolved F over here. Then you resolve mg. So the component of mg in this direction will become mg cos 37 or 40 joules, 40 newtons, whereas the component of mg in this direction will become mg sine 37. So that will be 30 newtons. Okay, and then you have your other force, the normal reaction, which is acting in this direction. Normal reaction is like this, and under the action of all these forces, body का acceleration कैसा है? It is along the x-axis. So along the x-axis, your net force will become F cos 37 minus mg sine 37. That is the net force. So that should be mass into acceleration. Whereas along your y-axis, your normal reaction should balance the other two forces. Okay. So this is your second equation. But this is not really necessary for us because we don't want to find normal reaction. We just want to find out. So from equation 1, we can see that the acceleration will become F cos 37 minus mg sine 37 divided by the mass of the body. So this is 50 into 4 by 5 minus 50 into 3 by 5, the whole thing divided by 5. So that's 40 minus 30 by 5, or the acceleration is 2 and the answer is in meters per second square. So this is the acceleration. Okay, because this is in newtons, this is in kilograms below the denominator. So anyhow, so now you got the acceleration. Now use kinematics. Use third equation of motion along a straight line. V square is equal to u square plus 2as. So it's starting from rest. Okay, and by the time it comes here, your displacement of 20 meters, you're wanting to find out the v. Now during that motion, we just saw that the acceleration is this one, is this value. Okay. So you'll get that v square is equal to 0 plus 2 into 2 into 20. So v is square root of 80 or 16 into 5, so 4 root 5 meters per second. So you can see that this process is more familiar to us, but at the same time it's much more lengthy. So gradually, we have to learn to make a shift from this method while solving problems to the work energy method, which gives us in one step. It gives us very easily in one step. So Anshul, you can understand all this in the recording later, na? Because you have just come from some tuition, I cannot change the pattern of the lecture. Na? You have to be a little bit patient. I'll finish this question with everybody and then start with the next part. In any case, next thing we'll be doing will be theory. We'll be understanding the concept of potential energy next. Okay, so people, hope this is clear now. Okay. So in this actually we are doing this first. This is the second thing we are doing. So this is what we are solving first, and from this we are applying kinematics. Okay, so this is an example of the application of the concept that net work done by all the forces is change in kinetic energy. Okay. Now from this we will move on to the next part of work energy theorem or work energy chapter, where we'll understand the concept of potential energy. From work done, the next thing we'll understand is potential energy. So the as per the definition, okay, potential energy is the form of energy, okay, for a system, okay, associated with its configuration, okay, or in simple terms its state. So this is the important thing here, that it is a form of energy which is associated with configuration. So first of all, it is defined for a system, it is not defined for a single body. So for example, if we have a block attached by a spring, okay, a spring mass system, so the elastic potential energy of the system, okay, which will be a form of energy stored in the spring, okay, so that energy depends on the state of the spring, state or configuration, okay, of the system. So in this case, what do we mean by exactly configuration of the system or state of the system? That is nothing but the state of the spring, that is whether it is compressed or extended. That is what we mean by the state of the spring, whether it is compressed or it is extended. Okay. Now, one more thing, potential energy can be converted into kinetic energy and vice versa, okay, readily during any process. So for example, here, if the block is made to oscillate, okay, then in the oscillation, kinetic energy converts to potential energy, and potential energy to kinetic energy okay, during the motion. So alternately, okay, cyclically, and you can say alternately. So first kinetic converts to potential, then again potential converts to kinetic, then again kinetic converts to potential. So alternately and cyclically, okay, this kind of change keeps happening. So that is the definition of potential energy, and this is an example of the potential energy of a system in which there is the elasticity of the spring, which is the internal property of the system, So the configuration of the system or the state of the system, or how much potential energy the system has stored, which can be readily converted into kinetic energy and vice versa, that will depend on the state of the spring. That is, how much it is compressed or how much it is extended by. Okay, now some formulae of potential energy. So there are few particular type of formulae that we have to know. So different types of potential energy. Okay. So the first one we'll learn about today is elastic potential energy of a spring. Okay. So an ideal spring has the following properties: that it is massless, okay, and obeys something called Hooke's law. So let's understand Hooke's law. Hooke's law is that the tension or spring force, okay, is proportionate to the deformation x. So by deformation, I'll tell you, we mean either compression or extension of the spring. So by Hooke's law, what we mean is, in terms of application, what we mean is that if this is the state of the spring in what is called natural length, L is natural length, or you can say uncompressed state, okay, then the tension will be zero in the spring. But compared to that state, if I now extend the spring such that its length has become L plus X, so I have to apply an external force for that, and that external force will be countering the internal tension in the spring, okay. So here X is the extension in the spring length. So Hooke's law says that the tension will have a magnitude which is directly proportional to the extension of the spring, okay. And with algebraic sign, it will be given by minus kx, where t is opposite to x in direction, okay. And the magnitude of t is proportional to x. So that constant of proportionality k, it is called the spring constant, okay. It is called the spring constant, and as you will understand here, it is measured in newtons per meter, okay. That is the SI unit of it. So we'll come to the formula of potential energy also, but to understand potential energy, first we have to understand the working principle of the spring, which is basically Hooke's law. So here we are seeing how Hooke's law works when a spring is extended, okay. We'll also see how it works when it is compressed. So make a note of this first. Spring mass system, Adinath, means when we attach a mass to a spring, okay. So a spring mass system is basically a system that consists of a spring or multiple springs attached to bodies or a body says mass. So that is the meaning of spring mass system. Okay. It doesn't mean a spring which has mass. Okay. The spring we consider will always be massless in ideal spring case. Okay, so next thing, the potential energy of a spring. So what happens is that the potential and just like the tension is given by this formula, the potential energy is given by the additional formula half kx square. So this is the elastic potential energy of a spring, okay, which is having an extension of x. So we will look at the derivation of this formula in 11th. It's a little bit more complicated, so we won't get into the derivation here, but we will learn to apply this formula. Okay, so just make a note of this, and this is where we'll stop the discussion today. And next time we'll pick it up from here and look at how to apply this concept of potential energy in systems where kinetic and potential energy are interchanging, like the example of the oscillation I gave you, and how to apply the statement of the work energy theorem in that case. Okay. So yeah, Anshul, make sure that you go through the recording of today's lecture, whatever part you have missed, and if you are not clear with something from the recording, just send me the doubts on WhatsApp. I'll explain that part. I'll give you some help on that. Okay. So that's it for today's class, people, and we'll pick it up from here next time. So again, next lecture is also going to be very important, and we are going to look at the conclusion of work energy theorem in the next class. So please make sure you revise this part. So this is the potential energy stored in the spring beta. So next lecture now we'll understand how to apply this in work energy theorem cases, like in an oscillation situation when potential energy converts to kinetic and kinetic reconverts to potential. So the formula of potential energy we'll use is this one, half kx square. Understood, Yuvraj beta? Okay, good. So that's it for today, people. All the best. See you next lecture, and come prepared with this part for the next time.